Hey everyone, today I'm going to talk about another algorithm to sort a unsorted integer array, which is called quick sort. So the basic idea for this algorithm is to sort a unsorted array so firstly, we're going to find a pivot element from this unsorted array and make sure all the elements in the left side of this pivot element is smaller than the pivot, and all the element in the right side of the pivot is all bigger than the pivot. And then we just need to find in another call stack function, need to find the pivot in the left side array and the right side array. So after n log n times, we should have this unsorted array sorted. So let's do some clarification for the question. So the input type is a unsorted int array. Output type going to be a sorted int array. We assume that this array can be an OR. So we can write the code for this question. The signature for the question going to be quick sort, and our input is a unsorted array, as we have assumed in the sanity check. So we said the array can be NOR, or array length is only 0. We can just return the array itself. And then to solve this question, we have to know what is the left boundary and the right boundary, so we can get the pivot and sort it by pivot. So I'm gonna need to use another help function also called quick sort. But in this one, we're gonna override it with a left boundary as a 0 and the right boundary as a read of length -1. After the function, we should have a sorted array as a return. Okay, and now I'm gonna write the private function for this quick sort, and the signature is an integer array int left and int right. Okay, cool. In here, we also need to make sure for the base case of this function, after we found the pivots, we have to sort the left side of the array and the right side of array. So we need to find the pivot position. So the pivot path, which coming from another private function, I'm gonna write later. We're gonna put the left boundary, left boundary and the right boundary into here. Each time we got a pivot position, and we call function for the left side and the right side from the pivot position. So the left side going from the left element all the way to pivot position without pivot itself. And another side is from pivot position, the next element to the pivot position, +1 to the right side. Okay, yeah, that's the main function. And after that, we should have all this pivot positions in the left side array and the right side array. And after this function, we should have a sorted integer array. And let's write partition function for here. So in this partition function, we're supposed to find the position of the pivot position and put all elements that's smaller than the pivot in the left side of pivot, and all the elements bigger than the pivot in the right side of the pivot. Okay, the input gonna be the int array itself and the left boundary and the right boundary. So in here, we want to make sure if the left boundary is bigger than the right boundary, which means we don't have element or there's only one element left, we can just return. And then we want to get the pivot. Which pivot? Ideally, it comes from a randomly averagely some number in the middle of the array. So in here, we can just write as this way: left plus we make sure it's integer. Use the function random. It will get a random number from 0 to 1, and we want to time a range, which is right minus left plus 1, which is the range of this input. And the value, we call it, no, so here it should be a index, IDX, yes. So the value gonna be the actual value in this index. This is step 1. Step 1, found the pivot. Okay, after we found the pivot, we want to swap this pivot number to the right. So we have right, we have pivot index. Okay, we swap that to the right, and we can do the operations from left boundary and the right boundary, which is one element before pivot. Okay, so in here, let's check the left boundary, which is still equals to the left, and the right boundary gonna be the one element before right boundary, which is right minus 1. Okay, and then we have to swap all the elements to the position they're supposed to be. Okay, while the left boundary is smaller or equals to the right boundary. Until the right boundary is bigger than left boundary is bigger than right, then we can stop it. And in here, we have to decide if the element is bigger, equal, or smaller to the pivots. So from the first element, if this element is smaller than pivot, which means is in the place we want it to be, we can just have left boundary move forward. And okay, and if the right boundary have this position bigger than the pivot, that is also what we want the element to be. We can just move the right boundary to the left. And in the last case, we don't have the element in the position we want it to be. So it can be the element in the left boundary is bigger than the pivot, or the element in the right boundary is smaller than the pivot. What we're gonna do is swap them from left boundary and right boundary. After you swap it, they are in the right position, so they can move forward or backward. Yes, we get it. After we do that, this is after the while loop, and we should have a semi-sorted array in here. And right now I have to step 3. The step 3 is to swap back the pivot to the position where all the element in the left side is smaller, all the element in the right side is bigger. So the place it should be in the where the right boundary is currently. So we can swap the right with left boundary. and return the left boundary, which is index of the pivot. Okay, we get it. Okay, so this is there is a small function here which called swap. I believe everybody able to write it, so I'm just writing it down very quick. It's basically swap two elements in the array. Okay. Right. Let's analyze the time complexity and the space complexity for this question. So in this helper function, we can see each time we call this partition function, and then so there is a partition function inside this quick sort, and we call it log n times. This is a binary times call it, so we can see is a log n in here. Time complexity and a space complexity. So we can see the quick sort itself is a log n time. We shrink the size 50% each time to the left and to the right. And the partition function here is basically using the most of time. Basically, time is caused in this traverse, or as we can see, the scan the entire array with a while loop. So it is O(n) time. So the total time is a log n times O(n) time. As we assumed, this random function here, we said averagely get the middle element in this array, but there is a very worst case. We got the smallest element each time or get the biggest element each time. So we can't averagely split this input array into two smaller averagely equals. We can't split this bigger array into a similar sized two array. So in the worst case, we don't have the O log n, which is the binary shrinking. So in this case, we will have, unfortunately, O(n). We can't split to two smaller ones, and the partitions still cost n time. So worst case is a O(n) square. And averagely, we got this. And the space complexity, let's see if we have used anything. Okay, so for the space complexity, we haven't used any extra data structure to store the data. So there's O1 in the heap. And for stack, the basic function, basic space complexity we spend on stack time is from here. So we called function, we have this function and called itself. The maximum depth of this call stack gonna be log n time. So the space is O log n. It's big O log n time for call stack. Okay. Thank you everyone for learning this algorithm with me. Let me know if you have any question. I'll see you next time. Bye-bye.